Hey everybody, it's Mr. Clausen. Just wanted to go through some practice on how to read a position versus time graph. So go ahead and put this graph into your notes. It doesn't have to be super detailed, just get what you can. I tried to go here that you can see it stays at 0 till about 2 seconds. Then the line goes up, and I tried to make that about 8 meters, and you can see that happens at around 6 seconds. The line stays flat at 8 meters until about 8 seconds, and then the line goes down a little steeper until 10 seconds. So I'd like you to do right now is just to see if you could describe the motion of this object on your own. Now, if you're watching the video with somebody else, now would be a good time to hit pause and have the two of you discuss before I give the answer. All right, so go ahead and hit pause, write down the answer, and we'll come back and see how you did. All right, so in this position versus time graph, what would the object's motion look like if this was the graph we were having? Trying to come up with a way for how to illustrate this, and this is what I came up with. Now, hopefully, you had something that looks like this. Our object today is this little man up here, this little moving man. Right now, you can see he's at position 0. This is negative, and this direction is positive. So how would the object move on a position versus time graph the way you see here? It would look something like this. He would stand still. He would start walking to the right or the positive direction until he gets to about 8 meters right there. He stands still, and then he turns around and comes back a little bit quicker. Okay, so let's hit some of the key points there. We'll go back, rewind it. So this blue line will move the man to where he was. So right now, up until about 2 seconds, nothing is happening until the graph starts to go up. This indicates that the man is changing his position, and it's changing it in the positive direction. So he starts to walk that way. Now, when the graph gets to this point right here, all right, so up here at the plateau, what happens there is since the graph is getting flat, that means his position is no longer changing, and so his position is remaining constant, even though time is still happening. We would say he is standing still, which he is. Now, when we come back over here, you can see that his position starts to go in the negative direction, so his position is getting smaller. And he's moving now a little bit faster because over here it wasn't as steep, and now it's a little bit steeper. So he's walking back faster than he did before until he gets back to the original position, and it took him about 10 seconds to do that. So if we put this all together, there he is. He stands still for 2 seconds, walks forward. He goes 8 meters, and it takes him about 4 seconds to do that. He stands still for 2 seconds, and then returns the 8 meters a little bit quicker than he did before, and it takes him 2 seconds to do that. So if you're putting this into your notes, which I hope you are, hopefully you have something that looks like this. So this would be a good example of how to describe the object's motion. Stood still for 2 seconds, then walked forward 8 meters in 4 seconds, stopped for 2 seconds, turned around and walked back 8 meters in 2 seconds. All right, now some of the questions you might ask here is, what is the distance traveled and the displacement of the man? So what you want to do is you want to take a look here at the graph, and we want to break it up into sections. So the first section we take a look at here is where he actually traveled some distance. Now we know from the video that this is 8 meters. So in that point, he traveled 8 meters in one direction. So put that right there. Okay. Then the next section we'd want to take a look at is if you look right here. This part he didn't travel any distance. He just stood still. His position didn't change. But here he goes back 8 meters. All right. So if we take a look there, he travels 8 meters back in that direction. So to get his total distance, all you do is you take the two distances he traveled, 8 meters plus 8 meters, and you get the total distance of 16 meters. Now, distance is a scalar, which means direction isn't as important. If we take a look at what is his total displacement, it can be, direction does matter. His total displacement is no longer 16 because the total displacement is his change in position. So if you look at the two sections of the graph where he did have a change in position, this first one, he changed his position because he went from 0 to 8. And so he had a positive 8 meter displacement. Okay, now keep that in mind. Up here, he had no displacement because it is flat. But when he goes up here, he started at 8 and he ended at 0. So what this means is he actually had a negative 8 displacement. And if you put those two together, you get 8 plus a negative 8, and that gives you 0 meters. Now, it shouldn't be too shocking here for his total displacement, because if you look at the graph, you can see he started at 0, right? He took a trip, and then he returned back to where he was. But this process of taking the sections and adding them together will work if you don't return back to your original starting point. So right there is our total change in position, 8 plus negative 8, or 0 meters. So that was just a review on how to read a position versus time graph and get distance and displacement from it. If you have any questions, I'll talk to you in class.